So dear student, welcome to this course. The course name is Aircraft Flight Control System Design, the Conceptual and Practical Approach. Okay. So I name it this Flight Control System course, not the Flight Control Law, because we will design the control law also and we will analyze the control law. We will check the behavior of the control law, how it is behaving. Okay. So that is why I have named this an Aircraft Flight Control System. And the course will be both conceptual and practical. If the scenario is the requirement is given and control design criteria is given, then how will you design the controller? That should be, in reality, it should be implementable, right? So there will be practical approach. Okay. So first we in lecture 1 we will cover the course introduction. Later I have given to you the content of this course. So I would like to just show you the control theory map, which is designed by Brent Douglas. The reference is given here. So you can see all kind of controller design what so far is in the history has been put in the single picture. So it's look nice, and along with the system also the control has been put. So you can see all the car also it is given, okay, and different fuzzy logic controller, model predictive controller, optimal controller, all the controller has been put in the single picture. Okay, so that gives you some kind of motivation, like how what so far work has been already done, although I will cover the history of the control system. Okay. So before moving to the actual aircraft control, see, for example, like I have an aircraft, right? I want to control my aircraft. For that reason I will design the controller, and that philosophy can be that I will tell you the later what kind of philosophy you will follow for designing a controller. But here you can take a surrounding example. For example, as a human, if you want to move from point A to point B, what you will do? Your eyes will sense where the point A is and where the point B is an intermediate point. Okay, and eyes will give the feedback to the brain, and brain will process. That is the controller. Where should go, right? And brain will tell you the actuator you should, and here in this case the actuator is leg only. So leg you will move in order to reach from the point A to point B. So that is an example of simple controller. Okay, so now you can see how the feedback is important, right? If suppose the eyes is not sending any data to you, will be very difficult to go from point A to point B, right? So feedback will improve the controller performance actually. If the baby is there, if the person is more than 20 years, there will be different of movement, right? So you can see that you can now have a sense of some kind of control power. For example, like if a person is more than 20 years young age, so that have a very good power in the muscle leg, right? So the control power is more in that sense. Okay. So for example, like if you consider the simple RC aircraft, small one, and you consider the bigger aircraft, in which case the control power is more? Fighter aircraft case, right? Likewise, you can have a feel for that control power, right? Okay, and you should know how to control, how to know what to control, how to guide using sensor, how to move the actuator, how to take the accurate measurement. All the things are important. Example, like if your eyes is not able to measure correctly, you will not be able to move from point A to point B. And we should know that even though if the eyes is giving you the feedback, but your actuator is not working, your leg is not working, you will not be able to move from the point A to the point B. Okay, so that kind of things we have to know. And most important thing, we should know first what to control. Here comes the concept plant and its characteristics. Now I will say, for example, if I know the point A, person A and person B, and person A nature is different and person B nature is different. So we have to understand the person A behavior and person B behavior, then accordingly you can control. Okay. So here plant characteristics and knowledge of the plant is very important. Without knowing the plant, you will not be able to control. Okay. For example, like I can run the bicycle, right? But I cannot fly the airplane because I don't know the plant characteristics in that case, in airplane case. So it is very important to know the first is प्लांट, व्हाट इज प्लांट एक्चुअली। नाउ फॉर एग्जांपल देखिए, आप छोटा सा एग्जांपल भी ले सकते हो कि क्या कहते हैं, अगर आप मान लो अगर घर में हो तो जो माँ है वो अपने बच्चे को समझती है अच्छे से कि कब वो चिड़चिड़ा है, कब वो रो रहा है, तो अकॉर्डिंगली वो कंट्रोल कर ले जाती है, ठीक है। अब अगर उसको शेर का बच्चा पकड़ा दिया जाए तो वो कंट्रोल नहीं कर पाएगी, क्योंकि दोनों डिफरेंट है ना, दोनों प्लांट डिफरेंट है। तो इसका मतलब ये हुआ कि प्लांट की जानकारी तो जरूरत है, पर इंडिविजुअल प्लांट जिसको आपको कंट्रोल करना है उसकी भी जानकारी जरूरत होती है, ठीक है। ओके, सो now you see, let us learn from our surrounding, including ourselves. We understand this thing. We try to learn from the nature as for. Okay, I have given you some example also, and then understanding, implementation, and execution. And we start with the mathematical model. See, aircraft is flying, right? That is a kind of model. But if you want to design the controller, you have to replicate the complete model in a mathematical form, right? So generally we say first order system, second order system. Why we generally say? Because what the actual system is flying in the air or running on a road, you have to model mathematically. Okay, so that is why we start with the mathematical models, sensor etc, and hence careful approach is essential, because during the modeling you have to take the proper assumption, and assumption should be make sense. Okay, you see, if you want to model the aircraft, you should consider the earth atmosphere. Okay, where the pressure, density, etc, you have to consider this planet only, not the Mars planet, not the other planet. Okay, so this kind of thing. But that means what you are assuming, say for example, like when you drive any theory, any mathematical formula, you have to make some assumption, right? So assumption should be meaningful. Okay, because if you make so much assumption, then later it will trouble you in the final product, and this makes it very challenging, and if you and interesting also. So now with the human and all, we have we got some inspiration, like this subject is very interesting, so now we can completely change from that perspective to this one. For example, like I want to control my aircraft, for example, like I want to control my aircraft pitch. Okay, so we should know first the desired response, like what you want to control. For example, you want to control theta 5 degrees, 6 degree, whatever, and then whatever the feedback is coming, you have to compare. For example, like this is an aircraft, I want to attend my aircraft to a 5 degree. Okay, so now what I will do to attend the 5 degree pitch? Okay, so that means 5 degree is a desired one. Okay, and every time what you will do, controller will try to deflect the elevator up, and why up, why down, that I will tell you later how the actuator is doing. Because for example, if I want to move from point A to point B, I will try to move my leg in forward direction, right, not the backward direction, right? So that is how the elevator up will give you the pitch up motion. Okay, so you are flying with the zero pitch angle, and now you want to attain 5 degree pitch angle, so you have to deflect the elevator up. Okay, and each and every time you have to sense the data. Okay, each and every time you have to send data, what is the aircraft, what is the state of my aircraft. Okay, accordingly you have to compute. Okay, and comparison means error, you are finding error. For example, like you are flying with a 0 degree pitch angle, and now you want to attain 5 degree. Now what is the error? Error is 5 degree, right? So this error, the controller, what you will do, this error will go to the controller, and controller will compute. All the mathematics is live here only, controller block. Okay, the controller will compute how much elevator I have to deflect in order to attain the 5 degree pitch. Okay, but 0 to 5 degrees certainly will not happen, it will take some time, right? So at the each time is instant, you have to take the measurement. Okay, elevator deflected, now aircraft attain 1 degree, measurement, 5 minus 1 4, again 2 degree, 5 minus 2 3, again 5, like that, 5 minus 5 0, error is 0. Computer control will tell that okay, you have achieved your what you actually want. Okay, so now this is a measurement, some kind of eyes, right? And this is the controller brain, right? Okay, and this is the desired response, point A and point B, right? Error you are compressing, right? And finally whatever output you are getting. Okay, for example, like here I am getting pitch angle, right? And now where is the plant here? Plant is this. Plant is this. Now, for example, let's say aircraft is flying. If you not deflect the elevator in a proper manner, aircraft can go into the worst condition, right? For example, if you give too much elevator, it will pitch up. So you are flying very beautifully, you are flying, but you have not used controller, you have not used your controller in a proper way. Okay, so that means you have to understand the controller and you have to use in a proper way in order to achieve the desired motion. Okay, so that is some kind of overview of the control. So with this motivation, now I have built some kind of motivation to you guys. Why the flight control system or control system is very interesting topic, because as a professor I have to give you the feel for that subject. If you people are not interested, so giving the lecture is meaningless. Okay, so that is why some kind of motivation I have created to you. And now what I will do with this motivation, what I will going to cover so far in the upcoming lectures, that we will discuss, and it might be possible that in the future some shift will be there. For example, instead of listing 20 lectures, I can take 21 or 22 ones, and ups and down can be there. Okay, but as of now, whatever in my mind, I will go through that. I have designed the control structure. Little bit modification you can expect in the future. Okay, but that's no problem. Only you will additional you will get. Okay, this lecture 1 is today is a lecture 1 course introduction. Okay, now in lecture 2 I will tell you the brief history of the control system, because history is very important. You have to know that what so far work has been done in the past. Okay, you should appreciate the work what so far as scientific research has been already done. You should know that what so far work has been done, and that will give the direction of the future. Like, okay, in future so many works is pending, so I can approach to this area. So history is very important. Okay, in lecture 3 and lecture 4 I will cover the introduction to control system design. I will tell you about what type of control system. I will tell you the classification. Okay, I will tell you the open loop and closed loop. All the things I will cover in the introduction to control system design. And now, when you have some introductory idea of the controller, and then in lecture 5 and 6 I will cover the control system design approach. I know the introductory part I know, but in general, I am not talking about here flight. In general, how will you approach the control problem? You have to understand the first order system, its response, second order system, its response, all the things we will cover in the lecture 5 to 6. Okay, now once our foundation, we will build the foundation up to lecture 6, general foundation, to move the actual part of the course, which is aircraft flight control system. So now, as I said that plant dynamics is required, you have to understand the plant dynamics. So I will tell you the in lecture 7 and lecture 8, I will tell you the aircraft model and its dynamics. Okay, general dynamics I will tell you, but we will take some example and we will design the controller, right? How the aircraft is behaving. Okay, that's a kind of thing. Dynamics model and dynamics we will cover. Okay, now what you want in your life, everything linear, right? हम अपनी लाइफ में कभी भी नॉन लिनियरिटी नहीं चाहते हैं कि आज ये हुआ कल को अलग हो गया. ठीक है, पैटर्न शुड बी लीनियर, राइट? सो दैट इज व्हाई जब हम अपनी लाइफ में ऐसा चाहते हैं तो हम प्लांट्स को भी चाहेंगे वैसा करें, राइट? सो इन दिस लेक्चर 9 to 10 I will linearize the system. Linearization means about one particular trim condition. Then I have used the word trim, right? So trim means your net force and net moment are zero aircraft flying, steady state level flight or climbing flight, but net force and net moments are zero. That is trim condition. Okay, it can be any speed. For example, design speed is flying, okay, or more than the design speed is flying, or near to stall speed is flying. Many. Okay, in that condition you can say angle of attack is this, pitch angle this. So there is another the trim condition. Okay, now when you linearize the system, and then for example like a actual model was non-linear and you have linearized, so you have two model, right? One linear and another one is non-linear. Now you have two model, one is linear and one is non-linear. Now I will apply same kind of input, both linear and non-linear, and we'll see the comparison, because I have to check it's my linearization making sense or not. For example, this is my non-linear aircraft and this one is my linear aircraft. So I will deflect the elevator 2 degrees, same here case also same here 2 degree, and I will compare both the response. When I see response, then I will compare the states, velocity, angle of attack, pitch angle. I will compare, and I will have a feel kind of okay. Plots are overlapping. That means linearization. I have done linearization. Good, making sense. Okay. Now once it has been done, then we have to study the flight envelope and control system design criteria, because flight envelope means at what speed region to what you will be allowable to fly and up to what altitude you can fly. That is a flight envelope. Okay, so you can see V and H graph, altitude versus velocity. Okay, now when you are flying a manual aircraft, you can deflect the elevator 5 degree, 15 degree, 10 degree. More deflection you can put on a control surface in order to get the flight. But see, non-linearity comes when you deflect more. अगर आप एलिवेटर थोड़ा डिफ्लेक्ट करोगे तो नॉन-लिनियरिटी कम रहेगी, ज्यादा करोगे तो नॉन-लिनियरिटी ज्यादा रहेगी ना. तो हम ऑटो पायलट में चाहते हैं कि हमारा काम स्मूथ हो. वी शुड हैव अ वेरी स्मूथ ट्रांजिशन, स्मूथ फ्लाइट, राइट. So we will limit the deflection of the actuator. Okay, so that is why you can see inside the complete envelope you will have a autopilot envelope. Now design criteria you should know, because when you design your controller and when you go for the certification authority, they will check everything. What is the response of the aircraft, damping ratio, natural frequency, everything they will check. Okay, sometimes they will check your code also. Show me how your aircraft is behaving. Okay, if you written in the MATLAB, okay, or any other framework. Okay, so system criteria should be, control system criteria you should listed, and I will tell you that control system designer, like how much gain margin you have selected, what is the phase margin you have mentioned, that will come under control system design criteria. And both certain and uncertain case, because when you fly you will never know when the disturbance will come. आप जा रहे हो, सडनली गस्ट आ गई, तो आपने तो उसके हिसाब से कंट्रोलर डिजाइन किया था, गस्ट को अकाउंट ही नहीं किया था, तो गस्ट ने तो सारा काम खराब कर दिया. ठीक है, तो यू हैव टू बी ready for the uncertain case also. Okay, so that means when I say control system design criteria, that means both certain and uncertain case. In lecture 12 to 13 I will cover the aircraft longitudinal autopilot design and analysis. Now listen, longitudinal part, what is this? Aircraft has a 6 degree of freedom. It can rotate 3 direction and it can translate 3 direction. You may go to my aircraft design lecture, I will explain. For example, like if you follow this right hand rule, so this pointing is x-axis, right, and this one is a y and this is z. So this is a positive, right, so this is positive x, positive y and positive z. So now I can say positive x, positive y, positive. Okay, now it can translate in this direction and this direction. Similarly, it can rotate in this direction and this direction. Okay, now when I say longitudinal, that means it will translate in this direction, and it will rotate in this direction. 3 motion, 3 degree of freedom, right? So that is called longitudinal. And similarly, we will cover in lecture 14 to 15. We will cover the aircraft lateral autopilot design and analysis. Lateral means this motion. This motion is lateral. This motion is directional. Okay. And in lecture 16 to 17 we will cover the aircraft directional autopilot design and analysis. See why I am writing analysis every time. We will design the controller, whatever, so for example we have taken, that I will implement and I will check how the aircraft is behaving. Okay, and in that there will be controller is sitting there. I will tell you that we will design the PID controller. We will tell you the significance of each gain, and for example, like we will also tell you that in a model loop simulation 18 to 20. Okay, model in loop simulation, that means your both controller and plant will be sitting in the MATLAB only. Here I am using MATLAB, that is why I am saying that key MATLAB. Okay, so in model in loop simulation we will show you the complete flight profile simulation. When I use the word trim, I have linearized about one particular trim point, right, using Taylor series. But aircraft has to fly many flight conditions, right? Starting from takeoff to climb, we can take a speed from stall speed to maximum speed, different angle and all. So many different trim points you have to find out. Okay, so that is why first you design your controller at a one particular trim point where you mostly fly. For example, like a cruise design speed you are cruising. So in that case, you will design the controller, and from this, keeping this information in mind, you will schedule the gain for the other trim point. Set to you, right, gain. Okay. So ultimately, we will using the PID controller or any the see. I can use the PID controller. I can use that NDI controller, INDI controller. Any controller we can use. Okay. But here the thing is, we are computing this elevator, aileron and rudder power automatically, right? So controller is a mathematical block. So any control approach you can use. So all the gain I will explain you later in the part. I will tell you the significance of the each gain, how the proportional gain is affecting your performance, how the derivative is affecting, and how the integral, why it call integral, why it call derivative, why it call proportional, and is there any relation between proportion to the integral or integral to derivative. That all the things will cover in the upcoming classes, because it is very important to know the gain and how to estimate the gain, what is the procedure of calculating the gain. All these things we will cover in the future lecture. Okay, so this is all about the course content, but and also okay, we'll take one more topic, we'll take one more what I have told to you, trim condition, right? So aircraft can fly different conditions. So let's say in this trim condition you have found out the gain, PID gain. If you want to find out the gain for the other trim point, then you have to schedule your gain, right? Okay, for example, like a this trim point I have found out the gain, and this trim point find out the gain. For example, like a 10 to different or more. For example, like a Tejas aircraft has a more than lakhs gain. Okay, so you know that if you have a set of trim point set, and each trim point where you have a set of gains, then in intermediate point you can schedule, right? Okay, you will schedule, right, again. So that then how the scheduling you will do, that also I will cover in the lecture, and I will give the feel for also is really gale scheduling is important for a very stable system or unstable system. You will see in an unstable system gain scheduling is very important. For example, like you have to calculate different multiple trim point, because the fighter, for example, like a fighter aircraft is highly non-linear, very unstable plant. So you have to calculate, you have to find out the different trim point. So scheduling is very complex. But for example, if say this is a very stable aircraft like a glider, then you will see even a single gain the aircraft is perfectly working, and very less gain scheduling is required, because your plant is supporting. So see, everything is ultimately na, if you know the plant, you will design the controller perfectly. That's ultimately. And each and every course there is a prerequisite. See, when I say controller gain and all, that means how you should have some knowledge about modeling, system modeling. You have to have a knowledge about ordinary differential equation. See, you will see that key in aircraft dynamics. I will tell you u dot, v dot, w dot. U dot means du by dt. Velocity in s direction, y direction, z direction. What is the order? 1. First order differential equation. So you should have a feel for the ordinary differential equation. Okay, and a good grasp of over a linear algebra, because you will find out the eigenvalue, eigenvector. When you linearize in the aircraft dynamics, you will have a different type of mode, Fugate mode, short period mode, and each eigenvalue will represent the damping and natural frequency. Okay, later I will tell you that how it is. And understanding of the nonlinear dynamics as well, because our plant is nonlinear, we have to linearize, right? So this is all about the course content, and these are the reference generally I follow. See, fundamentals of controls you can cover in modern control system by Ogata, and when you want to implement in your aircraft case, you can use reference 2, and reference 3 also is a very good book when you talk about the aircraft control. And reference 4 is also, because reference 4 contains both flight mechanics part and control part. So when you go to the control part, you have a lot of examples also, lateral autopilot, longitudinal autopilot. So reference 4 is also good. Okay. Similarly, say reference 5 is also good, and then you have some open course MIT, and there is a you can find out in the MathWorks there is a control system content. Okay. And in for a gain scheduling, you can follow the reference 8. I have a reference, I will send you the reference to you guys. And in reference 9, you can have some report where you can see that how longitudinal autopilot works in the Boeing 777 and different aircraft also. So that is mentioned in the reference 9. So thank you so much for attending this lecture, and from the next lecture we will start from the history of the control system. Thank you so much.